Welcome everyone here in the room and online for the CITA seminar. We are very fortunate to have Dr. Chang-Goo Kim with us today, who is visiting from the Department of Astrophysical Sciences at Princeton. Chang-Goo is very active in the field of theoretical and computational astrophysics, notably for the understanding of the multiphase ISM in our galaxy. Chang-Goo has developed a remarkable numerical framework called Tigris that allows him and his collaborators to understand how the star formation and the three-phase ISM are self-consistently regulated by gravity and stellar feedback using kiloparsec scale MHD simulation. I think today you are going to tell us also more about the new Tigris extension with explicit UV radiation transfer and photochemistry module. So please feel free to interrupt Chang-Goo if you have any questions during the talk, or you can write it in the chat and I'll pass them on to him. So if you're ready, Chang-Goo, please take it away.
Okay, thank you very much. Thanks for the very nice introduction. My name is Chang-Goo Kim. I'm Associate Research Scholar at Princeton, and I'm mostly working on the numerical simulations of the star-forming interstellar medium. And today, I basically talk about the galactic star formation rates and the multiphase outflows from these simulations. Although I'm basically geared this talk toward more like implication of this ISM study in the context of the galaxy formation models, but actually, I really like this. So my personal motivation on this study is because ISM is so beautiful, and it is really the kind of the object or the place where all these complex physics are interplay with each other. So I really like to talk about the details of the ISM also. So, but unfortunately also I didn't really make my trip long enough. So maybe I can come back later at some point. And also feel free to ask me any kind of the ISM related question. I will try to answer as I can. But this talk is mostly actually geared toward some galaxy formation applications. So starting from the large scale structure, the large scale structure is a powerful probe of the cosmology, as we know. And this is now a kind of the somewhat outdated example of this success. When you compare with this bluish color showing this galaxy distribution from redshift surveys, compared with this reddish color from the galaxy distribution in the Millennium M-body simulations, you see that somehow remarkable similarity there. So this is a real success, and that is a kind of one of the evidence why this lambda CDM becomes a kind of concordance cosmology. But there is a trick here. As I said, there's a galaxy distribution in the Millennium simulations, but actually this simulation is gravity only M-body simulations. To get this galaxy distribution from this M-body dark matter only simulations, you actually had to paint your dark matter halos with galaxies. In this model, actually they use a so-called semi-analytic modeling technique. But in most cases, anyway, in any kind of the galaxy formation models, they had to have some way to model, to convert some variance into the stars and distribute your populate the dark matter halo with some galaxies. So when you actually think about this, it's actually not a very straightforward process. So dark matter halo, you can first look at their distribution, mass distribution of the dark matter halos. The x-axis is showing the mass of the object, and the y-axis is showing the number density of that object. And the solid line, the yellow, green solid lines are halo mass function, the distribution of the halo mass, either obtained from analytically or numerically. They match quite well, so it's also good. But then, somehow I'm hearing some echoes. But yeah, but then when you compare this distribution with some observed stellar mass distribution, which is shown in red dots, you see the large discrepancy there, meaning that there are some difference in this halo mass function and the stellar mass function. One naive expectation is when you basically collapse this dark matter halos, the baryons will follow with this dark matter collapse, so that you can populate this dark matter into the baryons into dark matter halo and convert entire baryons into dark matter, the stars. Then you will get this purple line. It seems like it's still very different, especially at the low mass end and high mass end, saying that there's not all the baryons have turned into stars and galaxies. So there, it's basically when you accrete all this gas and cools this gas into the stellar or the ISM, not all this ISM actually in the disk has turned into stars, meaning that you had to push some of this ISM away from the disk, or maybe even before that, your CGM or circumgalactic medium hasn't actually cooled because of maybe either because of their long cooling time, which usually happens at the large high mass halo, or there are some mechanism that hits up this CGM. This issue is actually quite severe in this low mass halos because we are expecting that this, given their barrier temperature and the gas properties, they have enough cooling time. The cooling time is short enough to actually convert all the gas into stars, or the CGM has to be fallen into ISM. So there must be some other process that prevent this to be this star formation process in the disk. So especially in this low mass halos, we think this is the star cell feedback that actually doing this job. So that's what the focus of the current talk. And what's actually happening in the ISM is like this kind of the ecosystem. Oh, by the way, I had to mask the AGM part, which is not a topic. So, okay, now it looks much better. So you can see that this CGM, there are CGM, okay, this gas cools and will inflow to the galactic disks, forming the ISM. And some of them can actually even collapse for very dense molecular cloud. And the stars usually form in the molecular cloud. By the way, the star formation happens in the molecular cloud, not because it is the molecule is prerequisition of the star formation. It is actually a good tracer of the gravitational bound clouds. So anyway, it happens in this dense molecular cloud. And when stars form, it emits a copious amount of UV radiation to the surrounding medium and also drives strong stellar wind. And eventually it dies as a supernova. And those kind of strong energy injection actually drives a turbulence in the ISM and also hits up the gas, so that while this feedback is kind of the active, star formation is somewhat quenched. So then the star formation, reduced star formation means reduce the feedback, and then now the gas can actually cools again, and this cycles back through this ecosystem. So the details of this, how to model all these details is something that I want to discuss later in more details. But I want to first go through what is actually done in the galaxy formation models in the more larger scale simulations or semi-analytical model. So basically these small scale processes cannot be actually modeled directly in the cosmological simulations. That's the main issue. So the one way to do is basically adopting some empirical models. So for the star formation rate, this is a kind of one of the most famous scaling relation in the astrophysics, showing the star formation rate surface density, star formation rate divided by their unit area as a function of the gas surface density, total mass in gas divided by the area. And they have a very tight correlation. And this scaling relation actually tells you the typical time scale of the star formation, which is defined as a sigma gas over sigma star formation rate. And that is proportional to the scale, inversely proportional to the scale of the gas surface density. So many of you may now, okay, this relation actually reminds me that this time scale called so-called the pre-for time, because that has a similar scaling. So, and it is also quite well motivated physically, because this pre-for time is a time scale for the pressureless gravitational collapse. So you can think it as a natural time scale for the star formation. But in fact, when you actually look at the these star forming galaxies in more details, there are huge gap between this pre-for time and the star forming time scale. So this is now what I'm showing you is observations of the nearby galaxies, and each points are each galaxy. And the properties what showing on the y-axis is from the bottom is pre-for time, and the middle is gas depletion time or the star formation time scale that I defined there. And then the top is the ratio of these two as a function of their stellar mass. So the pre-for time is typically about 10 million years, which is also similar for our solar neighborhood condition. And as I said, then the star formation time scale, if you actually measure from this chemical symmetry relation, it is actually around the giga-year. And then if you actually get the take the ratio, that's a 1%. What this means is not really a pressureless collapse. It is actually the pressure that regulates all the star formation and all these processes. So that's the one thing. But in the galaxy formation model, it is basically currently using these empirical models with more like this ad hoc 1% parameters. The other empirical models that they mostly adopted in the galaxy formation community is this galactic wind prescription. So when you also, again, to try, if we want to not to turn all the baryons into stars, you actually have to either eject lots of ISM in the disk, or you had to limit the CGM from cooling. And this is again the stellar mass function compared with observation with the simulation. They matches quite well by mostly using this ISM ejective galactic wind models. But in observation, what we can actually see is there are these galactic winds in multi-wavelengths, and they are actually nearly multiphase outflows containing both mass-loaded wind together with hot energy-loaded wind. But this energy-loaded wind is kind of largely neglected in this modeling. So adopting these empirical models give you a nice, some nice scaling properties and matches with some observations, but mostly because they are tuned to match the observations. It is good, still good, very useful tools, but it's kind of the limit the predictive power of this galaxy formation theory. So one of the motivation of our work, and also under the collaboration, so-called this small collaboration, and also the learning the universe collaboration, is we want to build some subgrid model that is not based on the empirical relation, but based on this resolved ISM simulations. So this talk, I basically want to go through how I model this star forming ISM in the simulations, and then what kind of the theoretical background we can actually provide for this galactic star formation weight, and how we can actually characterize this multi-phase galactic outflows to be used in the large scale simulations. And if I have a time, I can also go through what can be the next step that we are pushing forward now. So let's think about the star forming interstellar medium. The main characteristics, the ISM is turbulent and also it's multiphase, and also the magnetized. I will not talk about the magnetic field things in my simulation, but we are doing the MHD simulation, so that there is a magnetic field. And to model this, basically we need to solve these MHD equations plus some cooling and heating processes. And ISM is actually highly dissipative, meaning that their energy loss timescale, cooling timescale, or turbulence dissipation timescale is actually quite short. It's shorter than the 10 million year, which was a typical freefall time. So meaning that, I mean, if there was any pressure, it could be actually go away within this freefall timescale, so that it is still have a problem. We, as I said, it's not a pressureless collapse from the observation point of view, but theoretically it can actually lose their energy within this timescale. So how can it be that inefficient in the gas consumption? That all comes through this feedback effect. And this feedback is highly localized energy injection, basically. But that energy injection is just so large, so that can expand, and then it basically affect larger volume very quickly. It means there are strong coupling between the small and large scales that we need to actually include. And all this means the physically grounded ISM modeling basically means we need to do some direct numerical simulations of this intricate coupling between the feedback and the ISM physics. But we cannot really resolve everything, even though even I try to focus more on small and smaller lesions. So there must be some of the subgrid modeling or some calibrated modeling based on the even smaller scale experiment. So especially for the feedback, we can consider stellar wind, UV radiation, and the supernova. And what they are doing is the wind-blown bubble and supernova usually expands to kind of the sweeps of the gas medium, and that can inject more and more momentum. And the UV radiation, they can basically hit the ISM, both neutral and ionized ISM. And they also do the, basically, they can ionize the neutral ISM. So to do that, we actually need to do more somewhat careful studies at the small scale feedback effect. So that requires some other idealized careful studies. Based on that, we now actually have some idea of how these things actually affect the ISM. The one is the momentum injection is actually mostly dominated by the supernova, not the wind. Second, the UV radiation is actually dominant heating source, especially the far UV radiation is dominant heating source of the warm and neutral ISM, while the ionizing radiation is kind of the important in disrupting the GMCs. So we basically choose among all these feedback process, we first choose the most important sources. One is a supernova. The second is the UV radiative heating. So the model that we are learning is like represent this kiloparsec patch of the galactic disk, including their background differential rotation. To do that, we solve MHD plus self-gravity in a so-called this shearing box model. Once we have this cooling and the gravity, we basically those regions can actually collapse and very quickly collapse, and that we cannot really resolve this self-gravitating collapse. So then we replace this region with the sync particles, and the particles will represent the star cluster. And then we apply some population synthesis model. Basically, we use the Starburst 99 model to get their supernova rate from this star cluster and the total phi UV intensity from their star clusters. The supernova is basically it's realized as some localized energy injection, and at a given our simulation and based on our previous idealized result, our resolution is high enough to resolve the this important energy conserving stage of the supernova remnant. So we can just simply inject the energy from the supernova. For the UV, we first don't really follow the UV radiation transfer fully. But what we are doing is basically summing up all this UV contribution and then take the mean intensity. We apply some mean attenuation model to convert that into the heating rate. So the feedback effect here basically is realized in two ways. One is this momentum, expanding momentum injection from the supernova, and the second is this radiative heating that changes with the star formation rate. So then what will happen in the simulation is you will basically cycle through or the star formation and then feedback, quenching, and star formation, all these cycles. And the movie that I will show you here is a kind of top-down view of my simulation. And that's I'm showing you as the color scheme is gas surface density. So first, when it actually starts forming these star cluster particles, that is kind of at the peak of the first burst. Now, once it forms, that these particles, star clusters, host the supernova, and also that all their contribution to the heating has increased. So the gas has been heated up, and then that basically somehow quenches the the star formation, and now it is experiencing some dip of the star formation rate shown on the top. And then once you also lose this feedback, then this gas can cruise back again, and then the forms star formation then starts again, and this cycles back through. So once we basically the star formation at a level that is quite consistent with what we can observe from the solar navel condition, which is shown as a horizontal red bar. More on that is now what I can show you is this side with edge-on views of the density projection and the temperature projection. So once it basically have this strong burst, you now see they are driving large-scale winds toward up, and at some point, it also this feedback has been quenched, star formation has been quenched, and then it falls back. But then another cycle of the star formation will drive another generation of the feedback and drive the wind. What we can actually see here is it is both hot and the cool gas that is flowing out, and most cool gas actually coming back as a fountain, while the hot gas is blowing away as a wind. So we basically have all this somehow basic process that is self-consistently modeled in the simulation. Now we go to basically do some parameter space study. So now we run the 7 different models covering the range of the, let's say, the mid-plane pressure on the x-axis and the gas star formation rate surface density on the y-axis. And the result is covering, we are basically, the result that I will show later is mostly from the 7 different models. Okay, so I will now go to the star formation rates. Is there any questions so far? Okay, great. So to explain this galactic star formation rates, as I said before, the pressure is the key, or the energy density of the ISM is the key. And that kind of the theoretical idea actually comes from the kind of 10 years of paper from 10 years ago, and we have developed many different models and refined. And then finally, we have now preparing another paper that is basically pedagogically summarize all this theoretical model, including this based on the calibration to this Tigris simulation results. So basic idea here is, okay, when you see actually this galaxy, they are always everywhere in the at least nearby present-day universe for the star-forming galaxies, meaning that this disk system is a long-lived system. In terms of the, let's say, momentum or this equation of motion or the conservation law of the momentum of the hydrodynamics, what this means is there is a balance between the pressure gradient or and the gravitational force. If we integrate that along the vertical direction, what this gives you on the right-hand side is the total weight. So you are sitting here, you basically feel all the weight from above you. That's the weight written in W. And then this pressure gradient becomes a pressure difference. But then if you actually consider the midplane to the some kind of high enough height above a few scale height of your gas disk, the pressure actually decreases a lot, so that this pressure difference is actually just midplane pressure. So that's where we expect this balance between the midplane pressure and the weight comes from. And you actually consider there are several sources of gravity, gas itself, as well as some dark matter potential and also stellar disk. You can kind of analytically calculate what that can be, and you can write down these somewhat simpler equations, which all depends on the, let's say, galactic properties, or more like actually observables. So using some observables, you can actually get some weight estimator. Now I call it as a P dynamical equilibrium, PDE. And then first to check whether this conservation law is actually, or this quasi-steady state approximation is actually satisfied in the simulation, we first compare the total midplane pressure with weight. And then then we also want to ask whether weight, this observational or simpler estimator can actually give a reasonable estimation to the weight. And basically this relation is pressure regulation that is demanded by your disk system. And then another important point here, so when you calculate this weight estimator, you actually have to include both gas and star gravity contribution from the star. Once you do that, from the simulation, we basically directly can calculate this weight integral as well as the midplane pressure. There are large scatter because, as you saw, this is not a steady state, the static system. It is very strong bursty system, but on average, they are in this quasi-steady state, so that this midplane pressure and weight are on this one-to-one relation on average very well. And then also when we compare it with the weight estimator, this also gives a quite nice result. So that's one part of this theoretical framework. And then the other part is, okay, then what sets this midplane pressure? This pressure has to be lost through cooling and turbulence dissipation in quite a short time. So that means there must be something that keep replenishing this pressure or energy density, which we assume that it comes from the star formation feedback. And then we can basically write down this kind of a relation. And there it is basically the key parameter here is this epsilon, which we now call it as a feedback yield, which is the ratio between the pressure, total pressure, and the star formation rate. And if we actually consider this total pressure decomposed into 3 different components, it is actually consists of the turbulent pressure and the thermal pressure and also the magnetic stress. So we can actually separately think about all this contribution. So for the thermal pressure, it has to be set by this balance between the cooling and heating. And for the heating, we know that this phi UV photoelectric effect is the most dominant heating source. Means that this heating efficiency, which is written as a gamma PE, is scales with the phi UV intensity, but it's not just simply scales with it. It is actually scales with it with some coefficient called, oh, this camera. So maybe I can just keep going. Okay.
I don't know what.
So is this camera or?
I guess they asked to lower your screen.
Okay. Yes.
And the screen below. I don't understand.
Yeah. Okay, maybe anyway I should keep going, otherwise I can never finish. So yeah, I mean, this 5 UV intensity, when there is this called the heating efficiency parameter that actually sets the what is the actual heating rate for given the 5 UV intensity. But anyway, there is this kind of the expected relation, and once you compare that heating with the cooling processes, mostly for the cold neutral medium, it is from the C+ cooling, and then you can actually set the what is the thermal or what is kind of thermal equilibrium pressure should be. That is must be in this range between the where the cold and warm medium can coexist. And then from this work, the more detailed calculation, what you can actually see is this thermal pressure actually goes with interstellar radiation field strength, meaning that your strong the radiation field gets stronger, the thermal pressure goes up because the heating rate goes up. So when we connect this with the star formation rate, there is this additional steps. So each star formation basically give you some given certain amount of the 5 UV radiation. But then when the ISM actually see this 5 UV radiation, that there was some radiation transfer effect, or this UV radiation has been attenuated. So that is called this F tau parameter. But then we basically, yeah. This F tau parameter basically what this says is this thermal pressure at a given star formation rate will be decreasing as gas surface density increases, because there will be more attenuation by the gas. So what we can do is we can actually estimate what this F tau will be, and we can use some simple radiation transfer model to get that. That's what we actually now have in these simulations. And then for the turbulence driving, it is basically set by turbulent pressure. It is set by this balance between the driving and the dissipation. And the driving rate, or basically the momentum input rate, is written in this way. So basically the vertical momentum that is given by per massive star, and then there are each massive star give you some certain amount of radial momentum, and there are when their stars form, there are certain fraction of stars will be in the massive stars, which depends on basically the IMF. And then this total mass of new star divided by area over time is basically star formation rate substance. And then as momentum loss rate can be written as this momentum divided by area per crossing time, or the turbulence large eddy turnover time for the turbulence dissipation time scale. And then if you rearrange this, you can basically get this as this basically the turbulent pressure, and then the above the injection rate depend on this P star over M star parameter times the star formation rate substance. So what is the P star? P star is basically the total radial momentum that you actually get from each massive star event, and the M star is what is the total mass of star you need to have this kind of the one event. So typical from the typical IMF, you can get it as M star is around 100 solar mass. And then the P star is quite insensitive to the environment and all the condition is order of 10 to the 3 solar mass times kilometer per 10 to the 5 solar mass per kilometer per second, so that it gives the P star over M star of 10 to 3 kilometer per second. So then you can get this epsilon expectation for the epsilon parameter that is around this value. And that's actually quite insensitive to the galactic properties. That's quite one expectation. And lastly, for the magnetic field, it is kind of the consequence of the complex dynamo process. We have all the components to maintain this magnetic field as a dynamo process, because we have a turbulence and also shear rotation. So then basically what we actually empirically know from the numerical simulation is they are mostly in equipartition. So that's again quite insensitive to expected to be insensitive to the galactic properties. And then we actually look at that, the epsilon or the feedback yield parameter for thermal, turbulent, magnetic as a function of this mid-plane pressure estimator. Then there are this strong dependence for the thermal pressure, but the very weak dependence for the turbulent feedback yield parameter. So magnetic field is somewhat messy because it also requires quite long-term evolution to actually reach their correct saturation level. But depend on some model, we actually couldn't really reach the enough level of the evolution. But still, there are mostly either turbulent dominated or they kind of begin to reach the somewhat saturated properties. So they can give a quite reasonable star formation rate. So by combining it, what we can get is this theoretical expectation or calibration of this feedback yield. With that, because the feedback yield is the pressure divided by star formation rate substance T. Basically, you can rearrange the equation. Star formation rate substance T is pressure divided by the epsilon. And this pressure, you can estimate it from this pressure of the weight estimator. Okay, so that's the kind of the idea. When you look at from the observation, you can measure this weight from the observables. Or if you go to actually cosmological simulation, you can actually calculate estimated weight based on somewhat larger scale properties, not actually the properties of your unresolved individual gas particles or gas resolution element. So then with that, you can actually get what can be the mean star formation rate substance. Should I care about chats or no? Okay. Okay, great. And then actually this relation, nice thing about this relation, actually, if you actually ask to somebody rearrange your equation again, then what you can write down is this star formation substance as a function of the sigma over some dynamical time scale. Now it's not just the free fall time, it is gas free fall time and including some contribution from the star and the dark matter disk, but still is a dynamical time scale. Then what you get is this sigma z vertical velocity dispersion over epsilon. And actually, I didn't actually talk you was the natural units of this epsilon parameter is a kilometer per second, and the typical value that I got was about 1,000 kilometers per second. And this velocity dispersion of gas is typically 10 kilometers per second. So it just naturally gives you the 1% of the efficiency. And that's basically saying it is the gas consumption is inefficient because the feedback is so efficient to recover all this pressure again. And now let's just compare with the observation. There are some points, the background points are from the recent somewhat resolved observations from Kingfish sample, Pang's sample, Thing's sample, etc., and the Edge Khalifa sample. And their relation, if we just use our Tigers relation, they also can pass through the mean relation quite well. And maybe just some simple constant value also give a nice expectation. So that's nice. So that now we know we can actually have some more theoretical basis on how to predict the star formation rate substance T, which maybe can be used to the galaxy formation models once you can have a recipe to measure this dynamic equilibrium pressure. But there is okay, I will maybe not really have a time to talk that much about that, so just skip that. But then now move on to the multiphase galactic outflows. So before that, is there any question about the galactic formation rate, star formation rate?
Also a question about turbulence. So actually, you produce the turbulent velocity of 10 kilometers per second, but at high Z, there's actually a sigma SFR relationship, and for some of the bursty system, you really have very large turbulence, and I don't think we are very clear what is the source of the turbulence.
So kind of the one part is this, there are some claims that it can go up to like 100 kilometers per second. But some of them actually comes, this observation and measurement actually comes from the ionized gas tracers, which can be higher has a higher velocity dispersion than this diffuse warm neutral medium and also CO type gas that is more relevant to this analysis actually. So, but still there are some trend or increasing trend as a function of the star formation rate subdensity, and we do actually expect that from the I think we mostly expect that from some clustering of the stars, the supernova. But to be honest, we don't really have a yet very strong robust theoretical explanation on that. But from our simulation also shows that this effective star formation of the velocity dispersion actually increase slightly with the star formation rate subdensity. But that increase is over like 5 decades of the star formation rate subdensity is from the 10 kilometer per second to the 40 kilometer per second. So it's very slight increase. And the efficiency per Kuiper time also expect to be increased, let's say, in the higher density region or galactic center region, so from the observations as well. So the 1% is just kind of some reference value, not really the actual quantitative value that I want to mention. Yeah. Okay, any other questions? Okay, let me move on to the galactic winds. Okay, I said there are 2 types of the winds that can actually regulate your baryonic cycles, and in reality, there must be both basically exist, and it is clear from our simulation as well. So if you look at their evolution, and maybe I can stop some point. Here, you see in the middle panel shows in the temperature, and it is just basically hot gas is expanding out. While they are doing that, they also goes together with this cooler component. So they just coexist. So we need to actually include both. And actually, when you look at what is actually delivered by different phases, they are very different. So the plot that I'm showing on the top is the mass flux as a function of the height. And the blue is cool component, meaning I'm defining it as a gas with a temperature less than 20,000 Kelvin. And the red is from the hot component, is more like 1,000,000 Kelvin gas. So the mass flux is basically dominated by the cool phase. Why? I'm looking at this energy flux, and also metals is basically delivered mostly by the hot phase. And this trend is still almost kind of the true for most of the conditions that we explored in our simulations. Again, now the top panel, what is showing is mass loading factor, meaning that the ratio in the log scale, ratio between the mass flux divided by the star formation rate. And there you see that as a function of star formation rate, this cool component mass loading factor is actually slightly decreasing, while this hot component is just flat. And maybe at very high star formation rate case, you may see there are hot components can deliver even larger mass flux. But then for the energy flux, it is always the hot gas that is dominating, and that's the important source of the heating for the CGM. But how to actually model this? Can we actually just divide it into the 2 components? Well, if we actually look at their distribution as a function of the outflow velocity, also in the log scale in the x-axis, and the sound speed on the y-axis, they still have a very wide, occupied wide range of the parameter space. So for the sound speed, you can convert it into temperature at around 10,000 Kelvin. It is about 10 kilometers per second. So this below this blue dotted line is mostly the component that I called as a cool. But you can see they have a range of the velocity. So not all gas actually can go far. Only small fraction of this one gas can go far. For the energy, they are kind of occupied in some particular parameter space, but still their range is quite large. So how to model this is actually, we think it is this distribution function that we have to model. So that's why we come up with some simple two-component distribution model, and that doesn't look very good, but it's still kind of do the kind of basic jobs in describing those properties. If you have that, what you can do is, okay, let's ask about the mass loading factor as a function of stellar formation rate substance T. And then now, if I just count everything that is moving with the velocity larger than 0, then this is the relation that I get. The blue points are actually from the simulation, and this solid line is from this summa crude model fitting. But then now you can ask, okay, what if you are in some system with the escape velocity of like 30 kilometers per second? You had to cut out all these things because they may not, they just basically mostly bounded in the simulation, in the disk, so not really contributing as effectively as a wind. So if you're actually cutting off, then it is this mass loading factor changes like that way. 100 kilometers per second, 300 kilometers per second, 1,000 kilometers per second. Yeah. Once you know this distribution, you can actually do all this kind of the jobs, and then you can actually model your wind more correctly with this distribution function. If you look at the energy loading factor, actually, because this is mostly comes from the hot gas, they are not really changing much. So energy flux, energy loaded hot wind component is quite simple actually to model. So there are two components you need to model, and the way that you can do is using this joint PDFs. That's our suggestion. And then we want to actually do this. Although we know this, we all know that actual implementation into the galaxy formation simulation code is also very difficult. Where this small collaboration comes. And then basically there are several working groups. Then our working group is mostly actually first run these simulations and characterize this. But then there are steps to the implementation, to the cosmological simulation. And once we have that, we can actually go to the other, some new parameter space where we actually need more careful characterization. So then we can actually do this kind of cycles back together. So actual implementation is actually not very straightforward, but still we basically working on this very hard, especially the postdoc Matthew Smith and the Drummond Fielding at the CCA, and Matthew is currently at Heidelberg. Lead this project called Arkenstone project. Not sure. I'm not really familiar with all these small things, so but they are very familiar with it, so they just named it. Arkenstone is something they said is some gem. This small very like actually really like this Arkenstone. So okay, but the idea is, okay, we have this two-phase wind model from the joint PDF. We can actually sample the energy flux and the mass flux from these models. But then actual implementation is not easy because usually what this illustrated TNG model does is basically decouple each particle with some given velocity, and then just with some that has a same the unit mass element. But because this unit mass element is quite large, if we actually want to sample the hot component, it's either very sporadic high energy chunk that you are launching, or you are not really launching much, basically. So there are new ways to treat it. So basically what we are currently doing is we launch these two components of the wind separately with a different mass resolution. And then we adjust their decoupling condition to make sure this hot gas energy can be deposited to the ICGM more correctly, as well as we are implementing this cool gas or cool component evolution based on the more resolved simulation looking at this turbulent radiative mixing layer simulations, so that we can model this cold cloud evolution in the hot wind based on this model. So it is quite preliminary still, but I think Matthew made great progress here. So what now you are seeing is now the scale is much larger than what I showed before. It's a 100 kiloparsec box showing an isolated galaxy evolution. And then on the top right panels, what you are seeing is now that there are this hot wind component fraction and this cold wind component fraction. And they are actually successfully launched this hot wind, as well as while they are doing that, this cold cloud formed, and as they evolve, their original mass actually changes. Sometimes it gains the mass from the mixing of the hot gas, and as it goes far and far, it actually loses their mass through the shredding effect of the sharp cold cloud. I cannot really say much about this because it's still in the premature, kind of preliminary stage, but it is very exciting. So we can, let's see what we can actually do with this model. So I think I'm on the hour, so maybe I can just skip this, or if you want, I can cover that some of this, but okay. Okay, so I mean that was all good for the Tigris, but then now we want to actually do more careful job on treating this cooling and heating process, especially including this UV radiation transfer. So this new extension, we now solve the UV radiation transfer using the adaptive ray tracing that is developed by Chang-Goo Kim, shown in the bottom left. And then once we have this information, and then we couple that with non-equilibrium chemistry of the hydrogen, as well as some equilibrium chemistry for the carbon and oxygen bearing elements to get this cooling rate and heating rate more consistently. So this new extension is huge work that is done by Chang-Goo together with us, and now it is in the stage of the preparing the final paper of this, but then we had some results apply this to our Tigris model. So now I'm showing you the evolution again from the slides of the side view, but there are now kind of the new field that now you can see, which is this in the fourth panel showing the phi UV intensity, the mean intensity of phi UV, and also on fifth panel showing this Lyman continuum energy density. So this both phi UV and EUV energy density is followed by this radiation transfer adaptive ray tracing. Then we can now do this, basically ask the same question, whether is this in the pressure regulated state? Yes, they are in the mid-plane pressure matches with the weight, and the weight estimator is still good. And then whether they are in the same relation for the turbulent feedback yield. I mean, they do show quite similar relation, but now we have a slightly higher thermal pressure, but it is mostly because the one that let's say the heating efficiency that now we get as a somewhat self-consistent calculation is about factor of 2 or 3 higher than before. So that's why we have this little bit enhanced thermal pressure. But important point is their scaling is quite similar, meaning that we had some attenuation prescription based on the uniform radiation transfer model, but that actually gave a quite good estimation. So this quite reassuring, and that particular analysis is done by grad student in Princeton, Nora Binger. So, okay, now we have this component that we can control more self-consistently. So now, okay, let's do some experiment. Let's turning on and off each component. That's what we did. So yeah, I can just show you that although they have when we basically restart this simulation by turning off the supernova or by turning off the UV radiation, they do have some initial bursty fluctuation. But this, in terms of the gas depletion time, which is inversely proportional to the gas surface density, it's just kind of the only around factor of 2 changes. So in other words, star formation rate is only enhanced only by factor of 2. If you lose either supernova, if you lose either UV, you only increase it by factor of 2. That is also because
this diffusion time includes gas of all phase.
It's all phase. Yeah. So the point here is there is no catastrophic failure. One reason is because they do, in particular, this model has pressure components has a quite similar level, although the turbulence is still dominant component, but the thermal component was not negligible. So if basically first, when you turn off the EUV ionizing radiation, which is now more comparable to the what we had before, that does give us similar results. So this is another, again, reassuring that what we did as a previous work was not that bad. Okay, and then now let's compare it with the pure supernova case. What is changed is basically this thermal pressure. The thermal pressure has dropped because has decreased because there is no heating, main radiative heating source. But because the turbulence can still be maintained by the supernova, and you only need to increase your turbulent pressure a little bit to compensate this loss of this thermal pressure. So that is just result in slight increase of the star formation rate. Again, if you just turn off the supernova completely, you basically lose your turbulent pressure. And together with also you are losing your magnetic support, because if there's no turbulence, this magnetic field cannot be maintained at the high level. So what you need is you need to increase your thermal pressure to compensate this loss. But another point here is because without actually strong turbulence, your disk is actually compressed, meaning that your weight is decreased. So you don't need to support as much as before. You only need to support the somewhat reduced amount of the weight with a somewhat increased thermal pressure. So that just make this star formation rate adjustment a bit softer. But what actually changed is ISM. ISM is different. On the top, on the bottom right, if you turn off the supernova, what you are losing is the hot phase. So each panel, left panel showing the temperature distribution, and the right panel showing the some defined phase structure. So this red, you lose all the red things, meaning that you don't have a hot gas. If you turn off the UV radiation, so you basically need to enhance your supernova rate to compensate your loss of the thermal pressure. So now your bubble is occupying more volume. Just if you don't just have a EUV, you are now losing all this warm ionized gas shown as yellow on the right panel, but they are more or less okay. But if you actually want to compare more with some high fidelity observations, like some future observations we are expecting from, let's say, the local volume mapper, we really need this full physics models to make some physical interpretation for this future high fidelity observation. So even beyond that, we can actually, what we can do is now we want to actually include this coursing rate transport to our simulation. So that's another active project we are working on with some more increased number of people in Princeton mostly. So yeah, that's something that we are doing right now with a new MHD code called Athena++. So stay tuned. Yeah. Okay, so this is a summary. Basically, yeah, this resolved star forming ISM simulation is important to really understand what's going on in small scales that is usually assumed by some empirical relation in the galaxy formation model. And we basically provide some more theoretical background and also some ways of implementing this without empirical tuning. So that's good. And then we want to actually develop this into the more realistic stage. So yeah, that's it for today. Yeah, thank you.
Do we have questions online first? I don't see questions in the room. All right.
Thank you for the nice talk. So so you mentioned that non-EQ is like one of the future direction you're going to do. So I think the non-EQ part you mostly do it with hydrogen, and then you don't for the metals helium you still don't like you still do like equilibrium chemistry. So what is the reason for this like different treatment?
Well, I mean, the computation cost we really follow. So adding each element requires additional assignment to the array, basically. So, and then once we have that, we had to treat their abundances as a non-equilibrium evolution together with basically they had to adapt with hydroflows, gas flows. Yeah, I mean, it's mostly one reason is mostly basically the computational cost, and the other reason is we think we know that this carbon chemistry timescale is actually quite short compared to this, let's say, the H2 formation timescale. So it is still fine to assume in some equilibrium state, although it may change with the conditions, definitely. So yeah. I don't know. I mean, for now, we are doing this with equilibrium assumptions, mostly basically computational reasons. Yeah.
So that's an implication, if I understand correctly, then the implication is that so when we predict those emission lines, metal emission lines, for instance, C2, for high Z galaxies, then if we apply a equilibrium model, so you think the result is still okay?
I mean, I would say it is okay, but yeah, I mean, in general, it's okay. See, the problem, maybe the most the problem is if you don't really have some correct internal structure of the ISM, then this gas, the UV, let's say the radiation field that is seen is very different. So if you're assuming this spherical cloud compared to this whole complex ISM structure, each gas that is seeing the radiation field that can change a lot. So I think that's more of the issue rather than the equilibrium chemistry. So yeah.
So there is one comment online, very interesting talk, the more or less alternating episodes of hot expansion versus cold fallback remind me of the cycles of supergiants pulsating star, but with several stochastic contributions to the outward pressure. Huh. Peter, go ahead.
Hi, Chang-Goo. Thank you. My first question is, what's happening to magnetic field as these winds are being launched. You have expanding magnetized bubbles like the old-fashioned Parker instabilities that are driven by pressure on the and mass loading on the magnetic field.
Sorry, I think I couldn't really understand your question.
What's the magnetic structure in the outflows?
I see what happened. I had my microphone buried in my closed laptop here.
Sorry. Yeah.
So I was wondering whether, as the winds are being launched, you're also taking magnetic field with it.
Right.
The old-fashioned Parker instabilities, for example, where there's mass loading on the field, but the field bubbles up into the halo.
Yeah, I mean, I think that's a very interesting project that I also have suggested for students, but no one actually have interest in that. So, so yeah, we couldn't actually proceed that analysis. So, but yeah, definitely it is interesting to look at how much magnetic flux actually goes together with winds. That's a definitely interesting question. I haven't really had a firm answer on that because we didn't analyze that yet. Yeah.
Another
Yeah, the second question, Peter, right?
Yeah, and another curiosity is you have this material that's flowing out, but then some of it's bound and you have it coming down, and we call it empirically intermediate velocity clouds. Do you have a good understanding of that through your simulations, how it changes phase as it's going up and down?
Well, yeah, I mean, let's say those intermediate velocity clouds that is, let's say, those shown in as a fountain flow in our simulations.
Yes.
Is mostly this warm gas, and I actually haven't looked at that whether they can actually form more like a cold gas in there, but given our current let's say treatment, it's not really turning their phase into the cold phase. One reason is because we don't really follow this phi UV structure that well, phi UV radiation field up there that well. It is still kind of uniform, so that this phi UV is not really very shielded, even though there are some dense gas surrounding, so that it is kind of very heated basically by the phi UV still. So it is all warm mostly, but not sure whether that is due to our kind of heating treatment or it is inherent nature of this IVC. Yeah. But
Yeah,
I don't see. I haven't seen any molecular gas associated with this IVCs yet.
Yeah. Well, I don't think too much is seen. We see CNM associated with it. But I was wondering whether some of it disappears from the neutral phase and you lose it for a while, and then it recombines as it's coming down.
Yeah, that's interesting. Yeah.
Wanted to ask, could you comment on what you might be missing and whether it matters by going to the shearing box simulation? So are there larger scale structures, inflow, radial motions within the galaxy? How do those, what could be different?
Yeah, I mean, definitely, that's a great question. And I definitely see there are some effect of the global structure, especially, I mean, accretion flow is something that I haven't really thought about, but like a spiral arm structure, and also maybe if we go to the galactic center region, and then that's also somewhat different story. So that we actually run several different simulations, one also having similar local approximation, but including the spiral arm structure. There, I can, yeah, basically once we have this gas is collected on the arm, it is it doesn't really increase the star formation rate that much. It just mostly reorganizing the star forming regions into the arm region. And then once we have that, and then once we apply kind of the, let's say the region by region, ask what is the vertical equilibrium for the region by region, it is still satisfied. And then what is the star formation rate as a function of the pressure, they are not that different. So mostly still they are quite similar. And then we also have other models with kind of the mimicking some bar-driven inflow toward the galactic center and forming the nuclear ring there. And then we basically do the study the star formation in these nuclear rings. And there we do see the, let's say, a bit lower feedback yield parameter, but parameter or other kind of aspects are still kind of hold quite well. So it is really the question. I think I can show you one thing, which is this one. So this is actually work done by the Sang-Hyuk Moon in Korea, or together with my former advisor Ung-Tae Kim. And yeah, the model that we are learning is like this kind of the simulation. So there are some inflow that is we are putting in, and then they are forming this ring structure in the galactic center. And then there are star formation happening in the galactic center. And then we actually looked at what is the effect of the changing varying inflow rates. With this black showing the constant inflow rate and the blue showing the varying inflow rate. And star formation rate is actually basically following the inflow rate. And then this just goes together with mid-plane pressure and then scale height variation. So then eventually, if we look at the comparing this physical expectation, first this mid-plane pressure and the weight, they are still kind of going together very well. So, and then once you do this similar prediction for the star formation rate, we do get quite reasonable matches. So it is really the question of whether you can be in somewhat quasi-steady state, meaning that your dynamical time scale, basically you are looking if you can average over your multiple dynamical time scale. That's basically where you can expect this quasi-steady state, and then all these things has to be matched because that is what is governed by this conservation equations. Yeah. So this feedback yield parameter can change a little bit because of the conditions, but that's one thing that we know about. Good thing about the supernova feedback is their momentum injection doesn't change much. It's not really sensitive to the environment. So that's mostly the reason why it's not, those can be applied in most cases. Yeah.
Okay, I think we should move to the after seminar discussion. Let's thank Chang-Goo again.